Good morning, HVAC team. So today we're jumping into unit 42. I will go ahead and share my screen. There we go. Okay, so unit 42 is fundamentals of psychrometrics and airflow. The objectives are discuss the factors affecting human comfort, list the ways body dissipates heat, explain the relationship between dry bulb, wet bulb, and dew point temperatures, plot points on the psychrometric chart, given any two variables, locate all unknown air properties on the psychrometric chart for the intersection, from the intersection of two known air properties. Calculate the mixed air temperature of two different temperature airstreams. Calculate CFM for or from velocity and area. And explain the difference between FPM, which is feet per minute, and CFM, which is cubic feet per minute measurements. Explain the difference between static pressure and velocity pressure. Okay, so air properties and airflow are the heart of air conditioning. It is important to understand air properties and airflow to be able to troubleshoot and maintain HVAC systems. Factors that adversely affect system airflow will also have a negative impact on the system's efficiency and reliability. Temperature is not the only property of air that is important to air conditioning. The properties of air include weight, volume, temperature, water content, and heat content. Humidity is nearly as important to human comfort as temperature. All the properties of air are important for the operation of air conditioning equipment. The study, the study of air and its properties is called psychrometrics. So that's that weird word if you haven't heard it before. All it is the study of the properties of air. So conditions of comfort. The body cannot be cooled by conduction, convection, and radiation whenever the surrounding temperature is warmer than the body temperature. They actually begin transferring heat in. Evaporation is the only body cooling process. The body has a remarkable ability to adjust to temperature change. When a person goes from a warm house into the cold outdoors, some compensation like shivering will occur to create body heat. So that movement is to create body heat. Your body just automatically does that. It's crazy. So yeah, conditions of comfort. Comfort is also affected by the level of physical activity. Activity creates more body heat, requiring more cooling to maintain comfort. So they got this little chart, which I like because it breaks down the levels of comfort and as it relates to your level of activity. So 78 degrees. So over here, it tells you comfort temperature levels for different activities. So at 78 degrees, that is optimal for bathing, showering, but sleep is disturbed. So, we all like a nice warm shower or a bath, but you don't want to be that same temperature in the bed. You'd be all irritated and kicking the blankets off you and peeling out of your pajamas and all that stuff. So 78 is good for the shower, but not so good for sleep. And then 75 degrees Fahrenheit, people feel warm, lethargic, and sleepy, but it's a good temperature for unclothed people. So if your house is 75, you probably ain't gonna be all that comfortable, but if you ain't got no clothes on, then you probably be just fine. 72, most comfortable year-round indoor temperature for sedentary people, meaning people that are sitting or still, no activity. 70 degrees is optimum for performance of mental work. And then 64 degrees, physically inactive people begin to shiver, but active people are comfortable, which is why like football players can play in the snow and not be too bad, not feel too bad because of their level of activity, whereas the people in the stands are shivering and barely getting through it. So yeah, so comfort is also affected by level of physical activity. Activity creates more body heat, requiring more cooling to maintain comfort. So air has weight, air has volume, air pressure changes at different, or air pressure changes at different altitudes. So like the standard, or the atmospheric pressure at sea level is going to be 14.7 psi. But the higher you start going above sea level, the lower that number is going to get. So anyway, the study of human comfort involves understanding how the area around a person affects the feeling of comfort and how the body adapts to changes in its environment. Normal internal human body temperature is 98.6 degrees Fahrenheit in the winter or in the summer. Body heat is produced by converting food energy into heat. There are 4 ways the body loses heat to the environment, and that's through conduction, convection, and radiation and evaporation. Air weight and volume. So they got dry bulb and wet bulb instruments obtaining relative humidity and value. So they got a picture of a little sling psychrometer right here. So let's go. So the air dry bulb temperature is the temperature measured on an ordinary thermometer. So when you hear the term dry bulb, they're just talking about the regular temperature, the temperature that's on the thermostat, or if you pull out a thermometer or your laser thermometer, your infrared, just the regular temperature in the room, that is your dry bulb temperature. And then instruments used to measure wet bulb temperature are called psychrometers. The most common psychrometers are called sling psychrometers because they swing in circles to help evaporate the water from the wet bulb. And so that's what the wet bulb temperature is. It's the temperature as it relates to the evaporation. Let me silence that. I actually happen to have a sling psychrometer right here. I never use it, but so there's 2 thermometers on here. This one's just a regular thermometer. This one has that little piece of cloth on it. They refer to it as a wet sock or whatever. So you wet it. It's right here. So you wet it, and then you swing it around in the air, looking crazy. And then you do that for a little while, and then you get your temperature readings. And your dry bulb temperature will be whatever the temperature is outside, and then the one with the wet sock on it is going to be a little bit lower, usually like about 10 degrees lower, because it's got that wet sock on it. And so that's a sling psychrometer. Never used it because I'm from the age where everything is digital, so I got a digital psychrometer, and you don't have to actually have a wet sock and all that. It'll just give you a digital wet bulb reading. I used to use my thermocouple though, which you'll get with your meters, and put a wet sock over that to read wet bulb temperature too. But anyways, that's a sling psychrometer. So the relation of the wet bulb temperature to the dry bulb temperature is a measure of relative humidity. At 100% humidity, both the wet bulb and dry bulb temperatures will be the same because water will not evaporate from the wet bulb. When a substance goes from liquid to vapor, that's when it loses the most heat. We know that from thermodynamics, from mile 135. So when a substance goes from from liquid to vapor, that's when it loses the most heat. So they're using that concept when they're measuring wet bulb, and as that water evaporates off of that wet sock, it's going to give off a lot more heat. So your wet bulb temperature is going to always be significantly lower than your dry bulb temperature because all that humidity is still there. It hasn't evaporated. So, so what was my point? evaporate. Oh, so at 100% humidity, wet bulb, dry bulb would be the same because it's not going to evaporate. At lower relative humidity levels, the wet bulb temperature will be considerably lower than the dry bulb temperature. Relative humidity value can be obtained by using either a wet bulb depression chart or a slide rule provided with the psychrometer. Dew point temperature. Dew point is another key air characteristic that is affected by the amount of water vapor in the air. The dew point temperature is the temperature at which the water vapor can condense out of the air. When air with a 55-degree dew point temperature passes over a 40-degree coil or evaporator coil, the water vapor in the air will condense to liquid and drip on the coil, which is why it drips down into the drain pan. So that's where condensation comes from. It's because of the dew point. Once that air reaches its dew point, the vapor in the air is going to condense into a liquid. That's why there's a drain pan under all the evaporator coils, because you got a 40-degree coil and you're blowing this warm air in there, and this air has a dew point temperature of 55. That coil is 40 degrees. That's significantly lower than 55. So once it goes in there, it's below its, once it gets in there and starts to lose heat, it's going to drop the temperature below its dew point, and the humidity or the water vapor that's in that air is going to condense, which is why the evap coil is always covered in condensation, and why you have to have a drain under the evap coils, and you have to pipe out your drain. That's where that condensation is coming from. And it's the same as how when you go outside in the morning and everything is covered in water, all that dew in the morning, that's simply because overnight temperatures got low enough to where it was the air reached its dew point, and all the water vapor in the air condensed into a liquid. And that's why you got water all over everything when you go outside in the morning. So the psychrometric chart. So this thing looks crazy, but it's not all that crazy. But it's right here. These are two examples of it. But the completed chart has all these lines everywhere. It's got vertical lines, horizontal, curved, slanted. It looks crazy, but it's just a chart like any other chart. As long as you look at what each area is telling you. Across the bottom, they're going to be telling you your dry bulb, and then across this side, it's going to be telling you your wet bulb, your grains over here, your enthalpy. Once you see all that stuff and you're trying to plot a point, it's just like any other chart. You just find point A, and then you follow it to point B, and so let's go through it. So the psychrometric chart is a graphical representation of air properties. Psychrometric charts are used by engineers to plot system performance when designing air conditioning systems. A system plot provides a visual picture of the changes taking place in the air passing through the air conditioner. The chart also shows the following air properties: dry bulb, wet bulb, enthalpy, dew point temperature, specific humidity, relative humidity, and specific volume. You can find all these different properties on the psychrometric chart, and all you need is two of them. If you have any of the two properties, once you plot that point on the chart, from there you can just follow it from that point to any of the other properties to find out whatever it is you want to find out. So let's say, for instance, if you have the dry bulb and the wet bulb temperatures, that's all you need. And then you could take that point on the chart and find the enthalpy, or find the relative humidity, or the grains of moisture, or whichever. It's all on the chart. So like I said, any two given properties is enough for you to figure out any of the other properties using the chart. So plotting points on the psychrometric chart. Any two properties that use separate lines can be used to plot a point on the psychrometric chart. All other properties can be determined once the intersection is found. So that's pretty much what I was saying. For example, the intersection of 80 degrees dry bulb temperature and 67 degrees wet bulb temperature is shown on the red dot in figure 41.23. Blue arrows from that point show the values of other properties at that condition. So one quick example that they show here would be, so you see how they gave us 80 degrees dry bulb, which is this line here, this vertical line. And then they told us 67 degrees wet bulb. So this is your wet bulb scale right here. So that's 65 and that's 70. So 67 is be right about here where this blue arrow is. And so that gives us this little dot right here. This red dot is right where 80 degrees dry bulb and 67 degrees wet bulb intersect. And then what else happens to be intersecting right here? We can follow it up this way and find our relative humidity, which is 50%. So, or if we wanted to find out grains of moisture, we could follow it out this way, and we're at about 78 like 78 grains of moisture. So you can find everything on this chart, even though it looks crazy. It's just a matter of taking what properties that you are given, which in this case was the 80 and the 67, and then from that point it's just a matter of finding, just tracing back from that intersection. All right. Sensible heat and latent heat processes. A horizontal shift, a vertical shift, sensible and latent changes. So again, these properties on this chart represent the actual properties in the air. So when things change on the chart, when you have a point, if you take your measurement at a certain point and then you take it again and it's at a different point, that's because the conditions changed in that space. Why did the condition change? Because maybe you turned the AC on, maybe you turned the heat on. So you can see those patterns by plotting these points on the chart. So nearly all processes will involve a change in sensible heat, latent heat, or both. The exception would be a process whose beginning and ending points lie on the same diagonal enthalpy line. Excuse me. Processes that cause a horizontal shift from the start to the finish represent a sensible heat change because the air temperature is changing. Processes that cause a vertical shift from start to finish represent a latent heat change because the air temperature is remaining the same while the specific humidity is changing. So let's take a closer look at that. So vertical, I'm just going right on through this, huh? This one. My bad. All right, here we go. So anyways, they were mentioning a vertical change. So if we look at point A and point B, there's a significant change in the grains of moisture. However, it's still sitting right here at 85 degrees. So no matter how high we go up this line, as long as we're on this line, we're still at 85 degrees, but other things are changing. Right here, the relative humidity would be 20%, and the grains of moisture would be, I don't know, like 50 or close to 50. But then, if you go up to here, our relative humidity is now 30%, and the moisture is a little above 60, or the grains of moisture is a little above 60. So what's happening from point B to A is, well, I guess it depends on which way you're going. Let's say we're going from A to B since A is before B. So if we're going from A to B, that's a latent heat change. Latent heat is heat that you can't sense. There's a change in heat energy, but not enough that's sensible, like to the touch or with the thermometer, but it's enough to remove humidity. So we're losing heat, and the humidity level is coming down. It went down from 30 to 20, but it's still at 85 degrees because it's still on this line. So that's kind of what they mean by when they say a vertical change on the chart, because these vertical lines represent the dry bulb temperature, which has not changed. So a vertical change would be representing a latent process. And then if we go over here, we have a horizontal change. So from point A to point B, this is a sensible change. We just went from 70 degrees to 88 degrees or 85 degrees. So this process is heat. Somebody just turned the heat on. So that's the differences, or the ways that you can see map out certain processes on the psychrometric chart. Where are we at? Oh, not there. Okay, and then the sensible change will be the difference in enthalpy from end to end of the horizontal leg. The latent change will be the difference in enthalpy from end to end of the vertical leg. So sensible changes are going to be horizontal. Latent changes are going to be vertical on the chart. And that's because no matter how high you go up the chart on whatever given temperature, like we saw, because we know the temperature is plotted out horizontally. So let's say you're at 90, but you shoot way up the chart from some other property. That 90 line is still 90 all the way down. You don't go up to 91 unless you're going horizontal. So these horizontal changes represent sensible changes, and the vertical changes represent latent changes. Okay, so plotting common air conditioning processes. The changes that take place in the properties of the air during an air conditioning process can be plotted. Figure 41.27 shows the addition of sensible heat. The process is shown moving along the horizontal line to the right. So in example 42 or 41.27, what am I doing? They're showing this process is heat. The heat is running. You're going from 70 to 105. So it's pretty open and shut. When you run the heat, you're going to go to your right horizontally across the chart. And then let's go to the next one. So figure 41.28 shows the reduction of sensible heat. This process represents cooling with a coil whose temperature is above the dew point of the entering air. So in this process, the cooling is on. We then went from 75 to 60. And they're showing even little graphics. So on the heat one, we had 70 degree air coming in. You see a little blower, and we got 105 degree air coming out. And over here, we had 75 degree air coming in, and then you see the little cooling coil, and the air is coming out at 60. So what's our next process? Figure 41.29 shows the addition of water. The action is represented by a vertical line moving upward as the specific humidity increases. So what would that mean? Somebody turned on the humidifier. So now over here we have a little illustration of the spray atomizer spraying water into the supply air. So it's coming in at 35 degrees dry bulb. 80 degrees, and then it's coming out still at 80 degrees because we're not doing a sensible change, we're doing a latent change. So we're still on that 80 degree line, but our humidity just went up from, well, they're not showing it, but like our grains of moisture went from 30 to 92. So there's a lot more moisture present in the air because of the humidifier. Figure 41.30 shows the simultaneous addition of sensible heat and water. The line representing the operation moves upward and to the right. So on this one, the zoom in. So the heat is on and the humidifier. So now we got 70-degree air coming in, 100-degree air coming out. So we went from 70 to 110 over here, and we went from 32 grains of moisture to 55. So that's with the addition of heat and the humidifier. All right, moving through it. Then 41.31 shows the reduction of sensible heat and water. This is the traditional refrigeration air conditioning cycle. The line representing the operation moves downward and to the left. That is what we typically are dealing with. That's the air conditioning process right there. We're dehumidifying and we're cooling. So you're gonna get a drop in humidity and a drop in temperature, because that's when people are more comfortable. So you got 75-degree air going in, 55-degree air coming out. You got the humidifier and the AC going. You just went from 55 degrees to 53. No, I'm tripping. No. They're not showing the temperature down here, but I don't know. Looks like that's probably like 75 to 50 something. And then our grams of moisture just went from 65 to 60. So that is the refrigeration process taking place right there. Actually, the humidifier is not on. I'm tripping. I misspoke. We're dehumidifying by cooling. So last one is 41.32, shows the process of removal of sensible heat accompanied by a simultaneous increase in water. The process uses evaporation of water to cool the air. So this one is using humidity, is increasing the humidity and dropping the temperature. So we went from, we went from 19% humidity to 80% humidity, with both temperature at 72, and our temperature went from 105 to 77. So this will be the process of removing heat and increasing the water. So those are different processes that you can see on the chart. Excuse me. So airflow fundamentals. The air in an air conditioning system moves. Rates are used to describe something that is moving. A rate measurement compares a quantity with a time. The output of a fan measured in cubic feet per minute, describing the volume of air in cubic feet that the fan moves every minute. The speed of the air is used to determine the amount of airflow. Speed is also stated as a rate. Airspeed or velocity is measured in feet per minute. Feet per minute describes how far the air will travel in a minute, but does not measure the amount of air flow. So CFM, cubic feet per minute, measures the amount of airflow. Feet per minute is how far the air will go. That's the velocity. Using anemometers and flow hoods to measure airflow. I've used both, and they're very necessary tools to have. Not most air conditioning techs have them. Air balancers use them. I mean, that's what they do. They check airflow all day long. But I don't think it's a horrible idea for a tech to have one. I have an anemometer. I don't have a flow hood, but I want one. I might get one. I kind of got a thing for just buying HVAC toys, because when you need it, you got it. I got stuff that I don't even use, but I'm just holding on to it for that one day when I need it, and I'm gonna have it, and I'm gonna save the day. So anyway, so anemometers measure air velocity. They are used to measure the velocity of air leaving registers and grills to calculate airflow. So basically, if you want to know how much air your system is moving, you got to go to each vent, every single one of them, and take your measurement with your anemometer or your flow hood, and then you total that all up, and that's going to tell you how many CFMs that you're moving. Every system has a capacity of air that is supposed to be able to move, and you want to compare that to what you're actually moving and see just how good or bad your duct system is. So taking accurate measurements is complicated by the fact that air does not travel uniformly through all parts of the register or grill, which is why the flow hood is recommended for checking air pressures, because it's designed to cover or to swallow the entire register or grill. So even though the air doesn't exactly come out evenly throughout all areas of the grill, you're catching it all anyway. So I don't care if you got a lot coming out of this side and a little coming out of this side. It's all going to funnel down that flow hood and then give you your measurement. So this can be remedied by taking several readings and averaging them. Some anemometers will take a real-time average, making this fairly easy to do. For calculating CFM, another complicating factor comes in, determining the area of the register. The only reliable method to look up the free area of is the manufacturer's literature. So basically it'll tell you the area on the grills, on the package that the grills come in. Flow hoods solve the problem of not knowing the free area by detecting all the air through an opening with a known area. They measure the average velocity and calculate the volume using the average velocity. So basically, the challenges you have knowing the area of the register, or the fact that the air doesn't come out evenly, all of that is eliminated when you use the flow hood, because everything just comes through that flow hood. Nothing is escaping. You're getting an accurate measurement, and it's going to take an average for you, and then you just move on to the next register. Types of duct pressure. Air moves through ductwork for only one reason. It travels from an area of high pressure to an area of low pressure. The blower provides the pressure difference to move the air through the ductwork. The amount of air the blower can move and the amount of energy needed to move the air is controlled by the resistance to airflow, the ductwork, and all the system components in the airstream. So that resistance to airflow they're talking about is static pressure. The word static pressure means stationary or not moving. Or sorry, the word static means stationary or not moving. When you blow up a balloon, the air pushes out evenly in all directions, creating static pressure. When a fan blows into a confined space, it creates static pressure on all the surfaces of the confined space. Velocity pressure is pressure created by moving air. Velocity pressure only pushes in the direction of the airflow. So again, the static pressure goes in all directions against the surfaces of the space. Velocity pressure is the pressure going in one direction with the airflow. Now I lost my place. Oh, okay. Velocity pressure only pushes in the direction of the airflow. If the end of an inflated balloon is released, the balloon will fly. It'll fly around the room because the pressure in the balloon goes from the high static pressure inside the balloon to the outside of the balloon, where the pressure is lower. Static pressure can be transformed into velocity pressure, as in the example of the balloon. Velocity pressure can also be transformed to static pressure. As a general rule, changes in duct geometry affect static and velocity pressure in opposite ways. Increasing or decreasing the amount of airflow will cause a proportional change in both the static and velocity pressures. Pushing more air through the same size duct will increase both the static and velocity pressures. Okay, now we're getting into how we measure the duct pressures. Duct pressures are read in inches of water column with an incline manometer, a digital manometer, or a Magnehelic gauge. So, inches of water column. They had these old school manometers, incline manometers, where you literally have this column filled with water. This one's got some red stuff in it, but it's full of water. As you, if you connect pressure in here, it's going to move that water up the column to a certain mark on that ruler, and that's going to tell you how many inches of water column that air just moved the water. So that's the, and this isn't even the original one. It's like a super old school version that they came up with, which is where that term inches of water column comes from. How many inches up that scale can you move that column of water with air pressure? That is your measurement. That's how they came up with that measurement, that form of measurement for air pressure. So now we use digital manometers that give us our water column readings without any actual column of water. But so these are the kind that I have. I got a field piece version of this because I'm a field piece fan, as you will learn if you don't already know. All my testing equipment is field piece, and then all my power tools is DeWalt. That's just what it is. Those are superior products. If you have a problem, maybe you at the wrong school. I'm playing, but anyway, I use my field piece manometer. It's digital. I use it not only to check duct pressure, but also the I use it to check gas pressure on furnaces too during the wintertime. This is a Magnehelic gauge. This is also a manometer. It's not called a Magnehelic. That's the brand name, but everybody just calls it a Magnehelic, but it's a manometer as well. The problem with these is that this needle never stops moving. When that air is flowing in there, that needle tends to bounce around, and then you have to pick an average. You got to kind of watch it go between 1 and 3, 1 and 3, and be like, okay, 2 is the average, or whatever. Digital manometers, they just give you an average. You don't have to sit there and watch a needle or anything. It's a lot quicker and a lot more efficient. It does the averaging for you. I still might get one of these old school manometers though, because all the old guys, they like them, they got them, so I might want to show off for all the older dudes I know in the trade. Plus, I just like collecting HVAC tubes. So anyway, reading duct pressure. So they're not showing the actual pitot tubes is what they're called that you use to put inside of the duct, but that's what I believe they're illustrating. When you take your pressure readings, you got to stick your pitot tube inside of there, and that tube is connected to a rubber hose that connects to your manometer. So anyway, 3 types of pressure readings are taken in a duct system: total pressure, static pressure, and velocity pressure. Total pressure is read by placing the manometer tube so that the air flows directly into the opening. So you stick your pitot tube in like against the airflow so that the air will flow right into it. The trick to measuring static pressure is to place the probe where it will not pick up any velocity pressure. Placing the probe perpendicular to the airflow is the most common method of reading static pressure. So now instead of going straight into the airflow, you want to go across it. And that's how you get your static pressure readings, when you put your tube in the ductwork. Velocity pressure cannot be read directly at a single point because static pressure is present any place a probe is placed. The velocity pressure is the difference between the total static pressure and the total and static pressure. Let me say that again. The velocity pressure is the difference between the total pressure and the static pressure, and could be read by subtracting the static pressure from the total pressure. It's that simple. Your total pressure minus the static gives you your velocity pressure. Reading duct pressure. Some Magna-Healy gauges and incline manometers are calibrated to read duct velocity directly in feet per minute. Most digital manometers can automatically convert velocity pressure to velocity. Calculating air conditioning system performance. So there goes those charts again. Don't get scared. They look crazy, but it's just a chart. It's just a bunch of lines that correspond with all these predetermined points, all the, temperatures, humidity levels. And all you got to do is just follow whatever line based on what parameters you have to work with. And you can find whatever's on that chart that you need to find. So the psychrometric chart can be useful in checking the performance of air conditioning equipment. When the wet bulb and enthalpy lines nearly overlap, the wet bulb temperature is really all that is needed to determine the enthalpy. 4 measurements are necessary to calculate the actual cooling capacity of an air conditioning system. Wet bulb temperatures of the entering air, wet bulb temperature of the leaving air, dry bulb temperature of the leaving air, airflow volume in CFM, entering air dry bulb if the sensible and latent values are to be calculated. An air conditioner is operating with a return air temperature of 80 degrees dry bulb, 69 degrees wet bulb. The supply temperature is 63 degrees dry bulb and 61 degrees wet bulb with an airflow of 850 CFM. To determine the sensible and latent capacities of the system, a third point is added from the right triangle, and this point is at 80 degrees dry bulb, 66 degrees wet bulb. The enthalpy at this point is 31 BTUs. So they're showing you that right here. So if we got 80 degrees dry bulb, what was it, 60 something degrees wet bulb, the enthalpy is 31 BTUs. Sorry, I was about to say degrees. 31 BTUs right here. So 80 degrees wet bulb, dry bulb, 60 degrees wet bulb, and we have our enthalpy at 31 right here. Let me go back and see what was on here. Nope. 80 degrees dry bulb and 66 degrees wet bulb. The enthalpy at this point is 31 BTUs. So again, we have our 80 degrees dry bulb right here, and our enthalpy, if we go, because this is our enthalpy scale, these diagonal lines. Our enthalpy scale coming from 80 degrees dry bulb, about 31 BTUs per pound. So moving on. Air mixtures. It is sometimes necessary to calculate the expected result of mixing two different air streams. Ventilation air in commercial systems is one example. Most codes require at least 25% fresh ventilation air in commercial installations. So basically, in commercial buildings, you need to be able to bring in 25% fresh air from outside, which is your makeup air. So typically, the air from outside is called makeup air. The air returning from the building is called the return air. And the result of mixing the two air streams is called mixed air. So in summary, the study of air and its properties is called psychrometrics. Air properties include weight, volume, temperature, water content, and heat content. Temperature and humidity are both important for human comfort. The weight and volume of air is affected by its temperature. The amount of water in the air is measured in comparing a regular dry bulb temperature to a wet bulb temperature. Dew point is the temperature that water vapor can start to condense out of the air. Air velocity is measured in feet per minute. Anemometers are used to measure air velocity. Air volume is measured in cubic feet per minute. Air volume can be measured directly using a flow hood. And total pressure is the combination of static pressure and velocity pressures. So that is psychrometrics for you right there. I know it's a lot to swallow at the moment, but the beauty of having this video is you can play it over and over. You can go over whatever key points that you want to go over. Also, read the book, because the book is going to take it even deeper. So the combination of the video and the book should prepare you more than enough for the review questions. And other than that, I hope that was helpful. Go ahead, hit those review questions, and I will catch y'all on the next one.